So to help you out with this sigma notation we keep throwing around, I want to suggest that you go to Appendix E. It starts on page A34, which is toward the back of the book. It's probably before the answers to the odd numbered exercises. There's a lot of great facts in that part of the textbook, and we're going to use some of those facts in a moment. Okay, so what does this theorem 4 say? If f is integrable on AB, then the integral from a to b of f of x dx is the limit, as n approaches infinity, of this sum from I equals 1 to n of f of xi delta x. Remember that this sum is an approximation by sums of areas of rectangles of the area under a curve. And this limit as n approaches infinity just means that we're letting the amount of rectangles go to infinity. And as you saw in those pictures in previous slides, the more rectangles you fit into the same space, the thinner and thinner each rectangle will be, so that as n, the number of rectangles, tends to infinity, you're going to get a more and more precise approximation until it becomes perfectly precise when you actually calculate the limit. Okay, let's try to rewrite this integral here in terms of a limit. Well, it's going to be limit as n approaches infinity of the sum from I equals 1 to n. I'm just basically copying everything that's here. My f of x is 4 minus 2x. So my f of xi is going to be 4 minus 2xi. And instead of dx, I'm going to write delta x. Now, my interval is 2, 5. How do I know that? I know it because this integral is going from 2 to 5. And I know that delta x can be expressed this way, and xi, I need a general formula for xi, can be expressed this way. So let's do those calculations on the side here. Delta x is going to be 5 minus 2 over n, which if we simplify is 3 over n. And then xi is a, which is 2, plus I times delta x, which we just figured out is 3 over n. So xi is 2 plus I times 3 over n. All right, now we're going to plug these two things into the formula we have here. And what we're going to get is limit as n goes to infinity of the sum from I equals 1 to n of 4 minus 2 times, what did we say xi was? Xi is 2 plus I times 3 over n. So this whole thing is being multiplied by delta x. Let's do delta x in a different color. So delta x is 3 over n. So we're multiplying everything by delta x, which is 3 over n. Okay. Let's simplify this and see what we get. Okay, so we're going to keep simplifying this until we get something we can work with. We have, let's see, we have 4 minus 4 minus 2 times I times 3 over n, all multiplied by 3 over n. These 4's here are going to cancel each other out. because it's 4 minus 4. And that's going to give us limit as n goes to infinity of summation from I equals 1 to n of negative 2I times 3 over n times 3 over n. Okay, let's simplify some more. We get limit as n goes to infinity of summation from I equals 1 to n of, let's see, negative 2 times 3, that's going to be negative 18. So it's negative 18I over n squared. Now, something to notice is that this sum is only going to be affected by I. In other words, I is the variable that's changing in this sum. N, as far as the sum is concerned, n is kind of a constant. And we know negative 18 is a constant, which means we can actually factor out this constant from this sum. We can't factor it out of the limit because n is still varying according to the limit, but we can factor it out of the sum. So let's do that. So we have limit as n goes to infinity of negative 18 over n squared times the sum from I equals 1 to n of I. Now take a moment to look in Appendix E for a helpful formula that tells you how to simplify the sum from I equals 1 to n of I. If you still can't find what you need in Appendix E, I'll give you a hint. It's Theorem 3 in Appendix E. Go find it. Make sure you understand what my next step is going to be. Okay. So hopefully you looked that up and or remembered it. This sum here is actually equal. So this sum, according to Theorem 3, is going to be equal to n times n plus 1 over 2. All right, so we're getting there. Okay, I needed some room, so I erased what I had so far. I have limit as n goes to infinity of, well, let's see, I can actually reduce stuff here. Negative 9 over 2 times n plus 1 over n squared. We have more things that can reduce. And this negative 9/2, it's actually a constant, which means we can factor it out of the limit. So let's do that. Negative 9/2 times the limit as n goes to infinity of n plus 1 over n. Okay, let's remember how to do our infinite limits. Well, I have n plus 1 over n. I can think of that as just n plus 1 over n. I can think of as n over n plus 1 over n, which gives me 1 plus 1 over n in the limit. As n goes to infinity, this is just going to stay 1. The 1 over n is going to approach 0. So that gives me negative 9/2. That's the exact number for the area under the curve of this function, x cubed minus 6x from 0 to 3. Now you should be wondering, why am I getting a negative number for area? Something seems wrong here, but I'll help you out with that in a moment. So why did we have a negative answer for something that I said was an area under a curve? Well, let's look at the graph of x cubed minus 6x. That's the function we integrated. From 0 to 3, we're just going to focus on that part of the graph. And let's shade the area under this curve. So when I say under this curve, I really mean the area between the curve and the x-axis. One thing to notice is that once we go below the x-axis, these function values that we're adding are going to be negative. So notice this pink area below the x-axis is much larger than this reddish area above the x-axis. The area below the x-axis actually counts as negative. And so what we have is we have a large negative number plus a small positive number, and that's why the total area ends up being just -9/2. In other words, it ends up being a negative number.